Imagine for a moment that we're standing in the middle of a spinach seed crop in Western Washington. The grower of this crop is right next to us, expecting to see a lush green field full of plants bearing seed, which would be distributed around the world to spinach growers who would produce the leafy green vegetable that we would later consume. But instead, this seed crop suffered a 75% yield loss. As we walk through the field, we can feel the healthy green individuals of the male pollinator on our left, yet we see the wilting, withering, and dead female plants on our right. The disease that resulted in this loss is called Spinach Fusarium wilt, which is caused by a fungus that lives in the soil. This disease is further exacerbated by the acid soils endemic to Western Washington and Western Oregon, which is the only region in the United States with a climate that's suitable for spinach seed production. In such conducive soils, the Spinach Fusarium wilt fungus can persist in excess of 10 years, which greatly limits the capacity for domestic spinach seed production. Now, despite the importance that this disease has for spinach seed producers in the United States, we still know very little about what allows this pathogen to cause spinach plants to wilt. But what we do know is that there are other closely related fungi to the Spinach Fusarium wilt fungus. These closely related fungi, some of them, are able to cause wilts on specific plant species. For example, there's a tomato Fusarium wilt fungus, and there's also a pea Fusarium wilt fungus, but there's many more examples. What we now know is that these different plant-specific fungi can be differentiated on the basis of a combination of genes. These essentially act as a genetic fingerprint. So in the same way that my fingerprint differentiates me from you, these genetic fingerprints differentiate the tomato Fusarium wilt fungus from a pea Fusarium wilt fungus. Now, my job as a PhD student at Washington State University is to decode the genetic fingerprint of the Spinach Fusarium wilt fungus. And by deciphering how this code is associated with this fungal pathogen, we can improve upon current management strategies for Spinach Fusarium wilts. For example, it's possible to develop a molecular tool that can be used to scan for the genetic fingerprint of the Spinach Fusarium wilt fungus. This would help growers in identifying fields that are at risk for this disease. In addition, by understanding the genetics behind this fungus, we can help out breeders in the development of better resistance to Spinach Fusarium wilts. And ultimately, all these findings together could help culminate in reducing the instances that we can see on the screen, where we're standing in a field with a grower and we see an enormous loss to a very important crop in the United States.